If you have ever tried to pair things up in the best possible way, you have already met the problem that Edmonds Blossom Algorithm solves. Imagine you want to match people into teams, students to projects, or tasks to machines, but not everyone is compatible with everyone else. Your goal is to create the largest possible set of non-overlapping pairs where no item is used more than once. This is called a matching problem, and when the connections can be messy and complex, Edmonds Blossom Algorithm is the breakthrough that makes the problem solvable. For YouTube viewers, the key idea to remember is this. Edmonds Blossom Algorithm is a method that finds the best possible pairing in any network, even when the connections form loops and tangled structures that break simpler methods. Before this algorithm existed, matching was well understood only in simple cases. If the network could be split into two clear sides, like workers on one side and jobs on the other, then matching was relatively easy. But real life is rarely that clean. Often, everything can connect to everything else in complicated ways. That is where the general matching problem appears. To understand the challenge, imagine a group of people where friendships determine who can pair with whom. Some people form triangles of mutual connections. These triangles are the heart of the problem. Simple matching methods get confused by them and may stop too early, missing better solutions. This is exactly what Edmonds Blossom Algorithm fixes. The algorithm was created by Jack Edmonds in the 1960s. His work was so important that it helped define the entire field of combinatorial optimization. The Blossom algorithm showed that general matching could be solved efficiently, not just in theory, but in practice. At a high level, the algorithm tries to grow matches step by step. It looks for ways to increase the size of the current matching by finding special paths in the network. These paths start and end at unmatched nodes and alternate between unused and used connections. If such a path is found, the matching can be improved by flipping which connections are used. This idea works well in simple networks, but in general networks, something strange happens. The search may run into an odd cycle, meaning a loop with an odd number of connections. These cycles trap the algorithm and prevent it from finding valid improvement paths. Edmonds' insight was brilliant and simple in spirit. Instead of fighting these odd cycles, he treated them as single objects. He called them blossoms. A blossom is an odd cycle that blocks progress. When the algorithm encounters one, it shrinks the entire cycle into a single supernode. From the outside, this supernode behaves like an ordinary node. This simplification removes the obstruction and allows the search to continue. This shrinking step is the heart of the algorithm and the reason it works when others fail. Once the blossom is shrunk, the algorithm continues searching for improvement paths in the reduced graph. If it finds one, the matching is updated. Later, when needed, the blossom is expanded back to reveal the actual matching inside the cycle. This expansion is done carefully so that all pairing rules are respected. You can think of blossoms like knots in a rope. If you try to pull the rope straight without addressing the knot, you get stuck. Edmonds' idea was to temporarily treat the knot as a single solid piece, pull the rope where possible, and then untie the knot at the end. This approach guarantees that the algorithm never misses a better matching just because of a tricky loop. One of the most powerful aspects of Edmonds' Blossom algorithm is that it always finds the maximum matching. This means it produces the largest possible number of valid pairs. It does not settle for a local improvement or a greedy guess. It systematically explores the structure of the network until no further improvements are possible. This makes the algorithm extremely valuable in real-world applications. In computer science, it is used in network design, scheduling, and resource allocation. In operations research, it helps optimize complex systems where choices overlap. In chemistry and biology, matching algorithms are used to model molecular structures and interactions. Even in social applications, matching plays a role in forming stable groups or partnerships. Despite its power, the algorithm is not easy to implement. The logic for detecting blossoms, shrinking them, managing alternating paths, and expanding blossoms correctly is complex. For this reason, many programmers rely on tested libraries rather than writing it from scratch. However, conceptually, the idea is elegant. The algorithm teaches an important lesson in problem solving. When something blocks progress, sometimes the best move is to temporarily simplify the problem, solve the simpler version, and then restore the details later. Edmonds Blossom Algorithm also changed how people think about efficiency. Before it, many believed that general matching might be too complex to solve efficiently. Edmonds proved otherwise. His work helped shape the idea that certain optimization problems are solvable in reasonable time, laying foundations for modern algorithm theory. For learning and teaching purposes, the algorithm is often explained visually. Watching how blossoms form, shrink, and expand makes the idea much clearer. This is why it is a great topic for YouTube content. Viewers can see how a confusing network suddenly becomes manageable once blossoms are handled correctly. In summary, Edmonds Blossom Algorithm solves the general matching problem by intelligently handling odd cycles. It does this by shrinking problematic loops into single units called blossoms, allowing the algorithm to keep searching for better pairings. Once a solution is found, the blossoms are expanded to reveal the final matching. It is one of the most important algorithms in computer science because it turns a messy, tangled problem into something structured and solvable. If matching is about making the best pairs possible, then Edmonds Blossom Algorithm is the key that makes perfect pairing achievable, even in the most complicated networks.